I'm Alberto Soto with Siemens PLM Software. Today, I'm going to present how to build a real-time compatible SimCenter AmSim model of an automotive cooling system loop. I will start with a classical model that can be quickly simulated, but which is not real-time compliant. Then, I will introduce, step by step, SimCenter AmSim functional components and compare both approaches. Here you can see the sketch of a typical automotive cooling system. In this example, the model features an oil cooler and the temperature is regulated with a thermostat. Let's now open a corresponding SimCenter AmSim model. The model consists of three main subsystems: the cooling loop in light blue, the engine thermal masses in brown, and the oil circuit in dark blue. Let's simulate a warm-up during an NEDC cycle starting from 25 degrees Celsius and have a look at the evolution of the oil, engine, and coolant temperatures. Despite a short simulation time, using a variable step solver, the model is not real-time compliant by nature. To ensure real-time compatibility, we can either apply different reduction techniques to the original model or rely on cooling system functional components. Let's focus on the second option and see how cooling loop, oil circuit, and oil cooler components help address real-time applications. The different subsystems of the reference model are replaced with these components while keeping the same boundary conditions. How is each subsystem's performance defined? Flow rates and temperatures are calculated, while pressure variations are ignored. The coolant flow rate is defined by two curves, in function of the pump rotary speed and the open or closed thermostat condition. These two curves can be easily built from the detailed model, considering the pump curve and the circuit pressure drop characteristics. The interpolation between these two curves is done automatically for intermediate thermostat positions. Regarding the oil circuit, the principle is quite similar. The two curves shown here were generated for two extreme oil viscosities. The other parameters defining fluid volumes, initial temperatures, and the radial performance data are limited to 13 for the coolant and 9 for the oil. Temperatures and coolant flow rates are very similar. In terms of the CPU time, the model using the functional components is about 10 times faster. Moreover, the model is now real-time compliant since we can switch to an Euler solver with a fixed step of 10 milliseconds. The temperature comparison between both solvers does not show any difference. Finally, we look at the elapsed time versus simulation time ratio. The minimum value is 500, thus showing that the model is largely real-time compliant. To sum up, with SimCenter AmSim, you can study and optimize the vehicle cooling system at different design stages, from pre-design up to control validation. From a detailed model, you will easily set up and run with a very limited number of parameters a functional, realistic, and real-time ready model. Thank you for watching. For more information, please visit our website.